Good evening. Can you hear me okay? Okay, I'm going to start desktop sharing. Welcome. Okay, can you see the desktop okay? Thank you. Let's see who's on tonight. Daniel, Fang, Karen, welcome. Before I start, do you have any questions? Thanks, Karen. Okay, on chapter 2, the thing I wanted to go over with you is it's basically a high-level look at all of the different elements of the OS, and I'm not going to go through the whole chapter, but I did want to pick up on something here. And when we were looking at it, we looked at it from quite a few different perspectives. So the operating system services, what kinds of services they provide. Can you name a couple? Hi, Linn. Does it perform process management? It allows programs to be executed. Okay, so that's a service, right? What's another example of a service? Well, maybe we should look at them. Support the I/O devices. Yep. I/O operations. File system manipulation, so that you can manipulate your files and your structure. And it provides a user interface, right? So there's a lot of services. Communications, to have one process share information between a computer. Error detection. We're having our test tomorrow, starting tomorrow, and open for 2 hours. So you want to have a 2-hour block sometime from Friday through Sunday, so that you could sit down and do the test. What I'm trying to do is go through some of the stuff that you're going to see on the test. A couple of other things it does is accounting. Keep track of what's happening where. I illustrated this, I think, with you guys. That if you go to Resource Manager, and you'll see all of the different processors. This is their process ID. And how many reads are happening, how many writes, and the access time for each of the processes on the disk. Same thing in memory, what's happening in memory. All of these things are being logged. What's happening in the CPU, the network, etc. Right? That's all part of accounting. And then there's protection and security. There's basically 8 areas of system services at a high level. And I think we went over them. There's 3 there. There's 2 there. And 4, well, 3 there. So what is that? 3 and 2. Something like that. Yeah. Okay. Now on the user interface things, right? Let's look at user interface. 3 mechanisms. What are the 3 mechanisms for a user interface? Anybody? Hi, Bale. I think I already said hi to Daniel. Fawad, hi. Saying hi. Yeah, I think I caught everybody else. What were the 3 different user interface methods? CLI, that's one, yeah. Command line interface. GUI, graphical user interface. And what was the third one? Whoop, never talked about it. The slides don't talk about it. No, not batch. I don't consider that a user interface. Now, I mentioned it when we were going through this. I wonder if it's in my notes here. No. No, it's not in my notes. Do you recall I was talking about being on a mini computer? AS400, System 34, System 38 from IBM. It was a specific type of user interface to that operating system. It wasn't command line and it wasn't graphic. Maybe this will help you. Watch what I'm doing. Remember now? Menu driven. That's the third kind. You don't see that much today, but it was really elegant. Okay, let's see what else we got. I'm just reviewing as I go through this. Okay, do you recall what the purpose is of a system call? Anybody, what's the purpose for a system call? Claude, you're right, but you're real close to the concept. I'm an application program, and I need to get something. Yeah, that's all true. I need some service performed for me. That's a system call. I need to call the operating system to perform, because I can't read a record, I can't open a file. My program has no access to the hardware. So in order to get to the hardware, I have to have a system call. And that makes it happen. So the purpose of a system call is to allow the program to gain access to some resource. Because you said everything correctly, that me as a program, I'm running in non-privileged mode. I don't have access to run privileged instructions. So in order for me to get the service, I have to call the operating system, which does have access to privileged instructions, and performs the service for me. So, and it ends up being an interrupt. That's the only way you can get to the operating system, is through interrupts. That's correct. So you all got a piece of it. But is that clear now what a system call is? It is typically implemented as an interrupt. But before the interrupt occurs, it sets up registers and things so that the operating system knows what kind of a service is going to go on. Does that make sense, everybody? Good, thank you. Good. And then what this is talking about is APIs. APIs are code that is provided in the language that we write in. That makes it easy, and we don't have to worry about writing code for a system call. This. We don't have to write this code that does this. Okay? All we have to do is use OpenF or read file. We use an API, application program interface, that builds this stuff for us. But if we didn't have APIs, we would have to do this. We'd have to do this stuff, okay, and understand how to do that. Well, we don't really want to get down into that level. This level is almost, you have to understand the operating system in detail to use this API. So getting back to system calls, I want to do read file or printf or openf in my programming language, and that's my API. I don't have to worry about how to actually perform the system call. In this example we did last time on Windows XP, and I was illustrating this to you guys. See, all this is set up by the compiler of this program. When the program was compiled, it set this up. And all of this stuff you see prior to the int21 and even after it, I guess, this is all set up to making the call to the operating system. And the int changes the CPU from user mode to privileged mode and goes to the interrupt address of the operating system that handles that interrupt type. And now I'm in the operating system performing the function. Then I get returned to the program. Now I'm back in non-privileged mode. Right here, non-privileged mode. I move, because I'm going to make another call, move, and then I make another call to the operating system. So immediately after one instruction, I'm back in the operating system, and the operating system is performing that in privileged mode, then comes back here, and after this interrupt, and does a push of the system's pointer, or stack pointer, and then continues in its code. And now I'm in non-privileged mode as my program. You don't see the operating system's code, but it's in this interrupt that occurs. I want to go over that again because I really want you to understand how that functions. I mean, to me, that's one of the key concepts. So here's an example of a system call, right? You got to do all this stuff to copy the contents of one file to another. Well, you might have a API that does a copy. You don't have to worry about it. Okay, we went through the example of that API. And I kind of showed you how it would get implemented. And probably this is the main thing. Most of the details of the operating system interface is hidden from the programmer by API. Are any of you guys taking C or another language, or have taken another language? Okay, what's the openf look like? Can you kind of write out what the code would look like if you were coding it on openf? Or in Java it might be open file. I haven't coded in Java in a long time. Well, I can tell you what it looks like in Visual Basic because I'm teaching that language this quarter. It's open file, file open. This is what the actual API looks like. Open file, file handle, so it's an integer, the file handle number. The file, oh wait, it returns the file handle. No, it's again, file handle. And then it's the file name. and then there's some access. So how do you want to access it? So access method you're going to use, is it sequential, is it random, etc. And then what's the access mode? Is it read, is it write, is it update? And that is the API call that will open a file in Visual Basic. And that's the idea here. I don't have to create an interrupt. I don't have to set up registers. I don't have to do any of that. The API does it all for me. So, using the API, I gave you open. This is open. It could just as easily been file open. That's my application. The API has been broken up into two parts. One part is it sets up all of the registers. It does all of this stuff. And then the interrupt takes it to kernel mode, and the interrupt says, oh, you want a service, and now it's performing the service. And then when it's done performing the service, it does a return, and it returns back to where the program made the interrupt, right after the interrupt. Okay? And now we're back in the user application. So this interface is something like this, looks just like this. And the system call is an interrupt. It's an int. It's an interrupt. That would be the system call. Is that clear now? Do you guys? How that works? Any questions? Is anybody puzzled? Okay. Well, we're going to go over it again and again, but I do want you to understand it. And there's printf as an example. Works the same way. The only thing unique is how do you pass parameters to one of these APIs? In other words, let me go back to the note that I wrote. These are parameters that would be passed to this API file open, and it could be just like this. It could be a list. It could be stacked, like this could be pushed on a stack. It could be in a register or a pointer, register pointer to this thing. Those are the types of things that he's talking about here, is how do the parameters get passed to the operating system to perform the function. And it could be a block or a table. It could be pushed on a stack, right? I mean, any of these are possible. It all depends on the design of the operating system. It also, the interface, right? The API could be created by the operating system vendors, or it could be created by the language, compiler language developers. Either of those could create the API. Just examples of if you pass by table. Okay. What kinds of calls are you going to make? Well, you might make process control calls to the operating system. When we talk about Chapter 4, thread management, you can create your own threads. Well, you call the operating system and it creates the thread, but you control the threads. So you could, in process control, create threads. A lot of it's file management, especially if you're in business, right? You're writing business programs. You spend your time opening files or databases or things of that nature. It's typically in this file management area. If you're a game programmer, right? Device like your well, joysticks aren't used anymore, really. They're more like these controllers, right? These different types of controllers. Well, those are device management type routines that you would use if you were doing games. I vaguely worked in the in the 1980s. I played a lot with joystick on a PC to see how to work the joystick devices. And joysticks had a special connection. They weren't connected, I'm trying to remember now, they weren't connected like a normal device. But anyway, information maintenance, you know, I want to know more about what's happening on my system. Communication, I want to communicate to another program. And finally, protection. So those are some examples of where a program would make a system call or an API call to get information. Any questions on that? Nice. I'm going to skip those. So there's examples. I'm not going to spend a lot of time on the details. Now we spent time on this. The difference between running Unity programming, one program at a time, versus running many programs. In my verbiage, a process is a program. And in almost every other one, if you have a program, let's say, let me look and I'll show you what I'm talking about as an illustration. Let's open a program. Yeah, let's do it this way. Okay, so I've got my processes here. I'm going to show all processes. This is just showing me right now, I think. Just showing me. Yeah, it's just showing the processes that I've spawned. Let's look at the systems as well. Okay, so there's looks like 122 programs that are running, 120 programs running right now. And I've ordered it by how much CPU it's being used. I want to do it alphabetically. And the reason for that is I want to go down to, I've got Notepad running here. Looks like I've got Notepad running, and that's this guy. Okay, it's executing. Let me start another Notepad. Okay, now let's look. And can you see I've got two Notepads running now? And almost all of these end in exe. So programs are equivalent to processes. And it's the same concept on most operating systems. All right, I want to close this one. So I could have multi-programming, meaning I'm executing these concurrently. And I'm using the word concurrent, not yeah, I'm going to just use concurrent. A little bit of processor time is going to each of these guys to run them. Remember, we're making the assumption that we have a single processor. There are system programs, there are a whole bunch of system programs that help in terms of the operating system. There's a ton of them. They do all this stuff that I just talked about. We spent quite a bit of time talking about user goals and system goals. Having goals is critical for designing the operating system, because when you have a certain goal, later on you're going to find out in the other chapters that various algorithms are available, but certain ones are chosen because of the goal. And we separate policy from mechanism. We'll talk about that when we come to security. Okay, a simple operating system is MS-DOS. Very simple. And that's the layers of DOS. Now, if you guys are interested, I offer this to my classes. Let me show you. I have the MS-DOS source code in a zip file. And if you're interested, you can see, here's 2.10 and 2.0. And these are all of the assembly instructions. And remember, each assembly instruction is equivalent to machine instruction. And it has each of these things. So if you're interested, I could put that on the website. Okay, I will do that. This is the copy to file copy, copy guide. We'll just illustrate it real quick. That is the assembler code that will copy a file. It's not very big. You look at it, it's not very big. Now, remember, in this operating system, DOS, when it does, let me see. I'm looking to see if it's got any interrupts. Yeah, it does. It's going to one handler in DOS. I mean, there are some handlers I'm going to talk about, but it goes to one handler. And all of DOS runs in privileged mode, because there was no concept back in the 1980s in those processors, 8088, 8086, of privileged and non-privileged mode. They didn't exist. So basically, when you were running any of your programs, you were running in you could execute any of the processor's instructions because there was no mode concept. That's not true today. Okay. Yeah, I'll do that, since somebody said they'd like to see that. It'll be a zip file. It'll look like MS-DOS.zip. And then you can take a look at it. I looked through it to see kind of how things work there in that environment. Interesting if you have time. But there's the layering of it. you're going to see this again. Matter of fact, this diagram is on the test. So I'm going to just say that it's there, and you need to understand these areas. Okay. This diagram is on the test too. You need to understand what this concept means. Now the microkernel concept is, kind of added on that you've got this little bit of code that just moves really fast. And it's easier to extend when you have a microkernel concept than having a kernel. I don't think this is on the test, so don't worry about that. I didn't put anything about Mac or OS X. Modules are kind of cool. In the operating system, and the same thing is true in Windows. If you need a module, you have to invoke it, you have to load it, and it extends the operating system capability. Or in the case of your program, it extends your program's capability. And usually they're DLLs, and I believe I showed you them before. I'm going to go to the C drive, Windows folder, System 32. And if we look down in System 32, there's DLLs. And that's the modular approach, that if that DLL is needed, it's loaded dynamically, because DLL stands for Dynamic Link Library. And we'll talk about this a little bit. I think it's in chapters 3 or 4, somewhere in there. But you can access them yourself from a program perspective. Has anybody used, in their programming language, have gone to use a DLL? Not yet. Okay. No. Okay. Let me illustrate that, because I could show you that. That'd be something I think worthwhile. In my Visual Basic 2 class that we don't offer anymore, we don't offer this class, but one of the requirements of one of their projects was to create a access to a DLL. I'm trying to find that project over there. Pretty sure it was this one. Oh, this is the registry one. No, this was accessing the registry. So it wasn't quite what I expected. Sorry about that. 3 wasn't, I know that. It might have been 3 minutes. Yeah. Oh, this is. Let me just check it real quick. No, I'm just doing access to a database. Yeah. Okay. No. I'd have to look for it, and I don't want to spend any more time on it. At any rate, it's that kind of concept. I'm going to skip Solaris. We spend a lot of time on virtual machines. I'm not going to spend much time on virtual machines. Okay, let's go to our notes. I think I covered the key points, so let's review. I covered Chapter 2. I want to go over the microprocessor specifications again. I'm not going to do hex dump with you at this point. It's not on the test. And what it is it's a program I wrote a long time ago that allows you to dump any file and look at it in a binary format. And I'm going to give you the code to do that, to have that code. And it's both a Windows version. Oh, I think it's a Windows version, and there's a command line version. So there's one of each of these. Okay, I do want to do this. Review the steps that programs use to access services. We've been talking about this. Okay, so let's look at the steps. I'm going to open up another notepad. Okay, so steps to access service from POS. Okay, so I have my program A, and it's running. Right, it's commands, it's running its commands, and it's running and running and running and running, and all of a sudden it wants service. So it's going to run an API, for example, open file, okay, and that API eventually is going to do an interrupt. Now what happens is in the CPU, the interrupt forces the CPU to do a number of actions. First action, it saves the current program counter to a special place in main memory. That's the first step. Step 2, it changes the non-privileged mode of the CPU to privileged. Step 3, it loads from a special place in main memory the address of the interrupt type generated. So basically, I want some service. in order to get to the operating system and get in privileged mode, the CPU does these things. So it loads into, I didn't say that, it loads into the program counter from a special place in main memory the address of the interrupt type generated, and 4 performs the machine cycle of a fetch. And what's happened now is, now we are in the operating system handler of that interrupt type and handle the request. And we're in privileged mode. We're in privileged mode. How to spell privilege? Privileged mode. When done with the service, we do a return. And the return, I'll just say what it's going to do. The return, it does other stuff, which we'll talk about in Chapter 3. But what the return does is load the saved program counter from main memory to that program and perform a fetch at some time sets CPU mode to non-privileged. So at the same time it does a load, it's a special command that loads the program counter from a certain memory location and sets the CPU flag to non-privileged, and then the fetch is executed. And now where we are, we're back here in the program working on that provided service. Working on our program, whatever it is, working on the data, whatever we needed. And that's how it's done. Now, is this clear? Any questions? Somewhat clear. Well, Steve, what's confusing? Where am I losing you? Okay. Well, once again, like I said, we're going to see it again and again and again. So those are the steps that programs use to access the service. Okay. All right, homeworks 1 and 2 and the CC Confer question due this Sunday, 2/21/18. We need to do the CC Confer question. No, we haven't done it yet. It's in this specification thing, which I'm going to go over next. But I wanted to make sure you understood that. Okay. All right. So let's open up the that particular presentation. I showed you this before. Then we talked about the processor. This is the diagram, the internal logic diagram of the processor. And what was important here was how interrupts are handled. So if you were a program in this environment, so let's get our notes up again. Okay. Now on this processor, on the RCA1802 processor, there is no privilege or non-privilege modes. Basically, everything runs at the same time, so we don't have to worry about that. So if we were looking at our registers, there's 16 general purpose registers. So I'm going to draw a quick okay, and then I want to copy this. Well, that's there. Try it again. Copy. And paste. Oh, I see why. I didn't do that. All right. So this is register 0. Register 1, 2, 3, 4, 5, 6, 7, 8, 9. It goes all the way to F, register F for 16. The thing to understand about the interrupts is this, which I'm going to show you right here. During an interrupt, so an interrupt comes in, someone, there's an interrupt line. Here it is, this guy. So an interrupt comes in, and we need to handle that interrupt. So what happens in the processor is P is the pointer. It's a 4-bit, and it's pointing to one of these registers that's currently executing instructions. X is a 4-bit register that points to one of these registers that may be accessing data with that program. Is that clear for you guys? Okay, good. This T, temporary, this T registers 8 bits. And it's only used for one function. It's only used for one function. And that one function it's used for is when an interrupt comes in. P is saved in the first part of T, and X is saved in the second nibble So P is 4 bits, it gets saved in the first nibble, and X is 4 bits and it gets saved in the second nibble, making a byte. And now, immediately what happens is P is set to register 1, and X is set to register 2. And whatever address is in register 1 is the operating system to handle all interrupts. So if I were designing the operating system in this chip, I would put the address of interrupt handler there. Okay, I would set the address here, right in here. All right, now the address of the interrupt handler is in 1, and I need to set the address of data handler for any of the data I want to handle in register 2. Therefore, if I were writing a program, an operating system, I would tell all of my programmers to always use register 3 and up for your programs. Don't ever use register 1 and 2. And this. They can use any of these registers for their program to run, but not these two, because I've got these over in my operating system. So I would have the address, if this was, I don't have a picture of memory. Maybe I can make one. Let me just copy that. Okay, so this address here, we'll go a little higher. This address may point to this handler. So here's my OS handler in memory. All right, and so what I would do, right, if I got an interrupt. So I'm running in one of these registers, 3 through F. Okay, this is D. And this might be dot, 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 dot. There's a lot more registers. Let me do it this way. There are a lot more registers. So this is 5, and then 6, 7, 8, and then this would be what? E. This would be register E. This would be registered E. So it'd be 6, 7, 8, 9, Abel, Baker, Charlie, Dog, Easy, Fox, or Echo, Fox. However you decide to use, or Delta, Echo, Fox, I guess if you're military, for hexadecimal numbers. But your OS handler, what it would do would be save T in memory and save any of the registers for that program, and then it could do the work it wanted to in registers 2 and 3. Excuse me, 1 and 2. 1 and 2. When I'm done, this is what's cool. When I'm done with processing that interrupt, I can do a restore. And what restore would do is I would restore the registers and then undo T. I would take the lower part of T and put it in P, the upper part of T and put it in X, and do the fetch. And now I'm back in my original program, handling maybe that interrupt or something. Is that clear? I mean, it may not be 100% clear, but at least you understand the purpose of T. The purpose of the T register is to save the current pointer to which register of 60 is running. It's a 4-bit, so it goes from 0 to FFFF. Same thing with the S. But I would have to tell, if I were telling people that write code on my processor, that you have to start at register 3. Register 0 is a special register. It is used for DMA. We haven't talked about DMA, but we will. And this is what makes this processor so powerful and so easy to use and build a computer around for somebody who doesn't really understand a lot about computers. Okay, any questions on this? Then let's go now to the question of the day, which is the weekly CC question. And you can do the question along with me if you want. I'll see if you got it right. And the way I set up these is that you can keep answering them as long as it's still open for that week. They opened at 7:30 today, and they'll close at this Sunday at 11:55 p.m. So, in the RCA 1802 architecture, when an interrupt occurs, the X and P 4-bit registers are saved in blank register. Then X is set to 2 and P is set to 1. Interrupts are disabled, and then a fetch is initiated. So what's the answer? Yes! 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 Very good. Doesn't matter if it's capital or not. Let's see if it's right. Hey, I got it. I got 5 points. So if you want to do it now to see if it works for you, I'll check the grades. I try to do this each time with the CC Convert. Good. Looks like I got Neil, and I got Junyi. Oh, Fang. I guess you're Fang. Do you want to be known by Fang or Junyi? Junyi. Yeah, come in as, yeah, Junyi, I got you down. Fang is the other person. Oh, okay, there is a Fang. I didn't know that. I know there was a Fang, but I didn't know that your last name was Fang. Let's see, we have a Fang. I'm looking. I don't see Fang. At any rate, let me do a refresh. And then we'll check one more time, and then that's it for this activity. And if you didn't do it now, you can do it later, okay, guys? Very good. Wow. 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 Nice. I'm impressed. Nice job. Okay. Did this example help now as to what was happening with this particular processor? It may. Okay. All right. Well, you have that out there. You have that. You can play, look at it. I've always found that if you looked at a simple concept first, when it gets a lot more complicated, it's easier to understand. So remember, these processors are 40 years old. Okay. Don't forget that you need to log in by, oh, you guys know, but anybody who's watching this, you need to log in by this Friday, tomorrow. Okay, I guess we could talk about the test. Before I do that, though, I guess I should go through these interrupt types with you. Okay, there are different interrupt numbers, and they specify types of interrupts. And I showed you a software request, int21. I showed you that. Request for operating service. There are also timer hardware interrupts, a timer, which is a hardware interrupt, and it updates the internal clock. So basically what happens, there's an internal variable. When we talk about the data structures in the operating system, we'll start doing that next week. We'll talk in Chapter 3 about some of the data structures. Well, there's got to be a clock that the operating system maintains and keeps everything updated. Well, what updates the clock is the fact that the timer is interrupting it periodically, okay? And it's about every n nanoseconds. We don't know how often the clock will interrupt the CPU. I mean, excuse me, the CPU interrupt will occur, and the operating system will update its timer. It's pretty quick. I mean, this doesn't take a lot of code. Now, when I request a file to be opened, or I request a file to be read, it starts an I/O device, and then the I/O device will trigger a completion when that I/O is done, and that's a hardware interrupt. It's called an I/O completion. Okay. There are software errors. Errors occur during the execution of instruction. Power failure. Operating needs to shut down prior to properly save what's happening in memory and stuff. It tries to, at least. Software trap. During the execution of instruction, divide by 0. The 0 flag is on, etc. I'll share this at the end because I think it's pretty, this problem-solving chart, I'll do that. Okay, I have another one of this. Program A is executing and using the registers. We know that T, yeah, I did that. I did that with you. Okay. If you kind of think of interrupts, there are two categories of them. One is internal and one is external interrupts. The internal interrupts are what would cause the CPU to interrupt internally while it's executing a program. Your program needs service. That's one that would cause an interrupt. That would be called a software interrupt. Could be called a service request, something like that. During the execute cycle, you could have an error. During the fetch cycle, you could have an instruction or data that's being accessed that's not in that program's memory. I know you guys are C, C++, a few of you guys. When I was learning C in the 1980s, I think no one was teaching me on this one. I spent almost a year and a half to write one program to learn C. And I always got memory protection problems because I was adding to pointers that were outside of the program's memory. That happened to me quite a bit. Of course, I was on DOS at that time. Those kinds of things would still cause an error today, but you wouldn't bring down the system. External interrupts are outside of the CPU. I mentioned the timer from the clock on the motherboard typically. I/O completion, I/O completed, power failure, keyboard, mouse, etc. Those are all types of interrupts. Okay, I've went through all of that with you. Let's see what's on the test. It opens this Friday through Sunday. There are two, quote, quizzes or tests. So let's make sure you understand that. There's test 1 that's required, and it's got 45 questions, and each, well, no, it doesn't have 45 questions, I'm sorry. It's worth 45 points, and I'll explain how the questions are inside there. And then you have one question, optional, worth 5 points. And you may or may not want to do it. It's up to you. But you will get partial credit if you try it and it's making some sense to me. So let's look at what's in the regular case. You get 5 true and false worth 1 point each. So you're either right or wrong. And you only get one shot at this, guys. So when you submit it, it's done. When you submit it, it's done. You can't go back and fix questions you missed. You get 5 multiple choice worth 3 points each. So you've got to really be, cautious on what you pick. And the way I write multiple choice questions is you only have one correct answer. I don't write them so that you could have well, A and D are correct. I don't write questions like that. It's kind of dumb in my mind. So there's only one correct answer. Then you have 5 essay questions worth 5 points each. And you want to be as thorough as you can be. Now I'm going to tell you here with these to not copy answers from internet. I will know that. You will get 0 points. Okay? Do not copy answers from the internet. Could you look at the internet and then reword those into your own words? Well, of course you can. Just like you can look at our notes and reword them in your words. But do not copy from the internet. I will know. Yeah, I've taught this class since 1983. So I think that you can give me some credit for knowing when an answer comes from the internet. And that's going to be the test. Are there any questions about the format? So plan 2 hours sometime. Now, will you need 2 hours? I doubt it. I really have always planned for the word that. When students were taking this class, when I was doing this class in school at the ANSA, they would take about an hour on average, even less. Because true and false, how long does it take to answer that? Less than a minute. Multiple choice, okay, I'll give each one a minute. That's 5 minutes. So together, that's 7 minutes. To write 5, it might take you 5 minutes each. That's 25 minutes. You could finish this test in about 45 minutes. No, Kang, it takes about a day for the recording to get created. So no, it won't be posted tonight. Is that clear? Okay. Yeah, I don't have any control over. CC Confer will put it on their site sometime, and you could, if it's available, you could access it. And then there's 3C Media that takes it from their site and converts it into YouTube format, and that usually takes 24 hours. So the CC Confer might have it at the end of tonight. I don't know. I've never checked. But I do know that the YouTube version of it, the YouTube version usually takes a day. This session stuff. But as soon as I get it, I'll check tomorrow. I'll post it probably midday tomorrow if it's available. I always check. You know, I'll check every hour or two to see if they have it posted. Since I've retired, so I don't have to do other work. Although my wife wants me to do stuff. Right?
Check the list.
Check the list. She's right here sitting with me. She knows round robin really well. You'll see round robin algorithms. She knows that really well. Matter of fact, I think she knows this operating system stuff pretty well too, because she's heard my lectures for many years now. All right. Let's see. What else was I going to talk about tonight? Oh yeah, I showed you a couple of things I wanted to share with you. I was probing around for types of interrupts and how to handle interrupts and stuff, and I ran across a couple of fairly decent articles. So I'm not going to put them on Canvas. What I'm going to do is just stick them here for you. So you've got that link you can look at. Okay, there's one. That was pretty interesting if you wanted to see what an interrupt is, type of interrupts, how to handle them. Don't download stuff, okay? I'd stay away from that kind of stuff because they're going to want you to buy something. But if you just read the article, I think that's good. Here's another one. I'll put that on for you. It's a PDF. And it's talking about this programmable interrupt controller, this PIC. And it was one of the original ones that came with the IBM PC. So as you can see here, these are the older processors. But it kind of explains how it works. And basically, it's another kind of computer, if you think about it, because you program it to handle interrupts, and you would program it with the addresses of what handles what. It's a pretty cool device. So a lot of today's processors get this controller, and it's on the motherboard. So you don't really see it as a chip anymore. Then there's types of interrupts and how to handle it. Is that what I have? Oh, then there's this one. I didn't show you this one yet. I'll just explain it real quick. Okay, spend a lot of time. But interrupt request architecture, these here are really cool to know. They're called interrupt request queues, IRQs. And there were 15 of them. Is there 15 or 16 of them? 16 of them, 16 queues. And look at the first queue. It's the system timer. So this interrupt was a system timer interrupt that would then go and be handled by the little bit of code needed to update the clock. And the clock is down here. You can see the clock on my machine. It's changing every second, but it's being updated. This clock internally in the operating system is being updated every X nanoseconds, whatever that setting is. Then you've got your keyboard for your keyboard controller. Then this got a little more complicated. Okay, so they cascaded these interrupts. And then you got your serial ports for your port 2, port 3. And serial ports were used for, back then it was used for your mouse. Your mouse was on a serial port many moons ago. And then your parallel port was your printer port. We don't tend to well, I guess we use it for sound today. For sound, we use that. And then you have your floppy disk controller. So these were basic interrupt requests queued up and with a number. Okay. And you can read through that. By the way, in the older operating systems, you could, when you look at a device, you could see what IRQ it was on. Today's, they don't seem to tell you that. All right. Well, I think I've covered quite a bit of hardware with you. We'll now spend more time, less time looking at the hardware and more time looking at operating system internals, like memory management, processor management, file, I/O management, that kind of stuff. Any questions on Chapter 2 stuff? Okay. Unless you have some questions, I think I covered everything today that I wanted to cover with you. Oh, I know what I wanted to do. Let's get this. Problem-solving chart. I don't know if you guys have seen this before, but I saw this in the 1970s when I first started programming. Have you guys seen this before? Anybody? Nobody? Yes. Okay. One person? Okay. You know about flowcharts. The way flowcharts work is they have a question and the answer is either yes or no, right? Okay, so if you're trying to solve a problem, does the damn thing work? Yes. Don't mess with it. No problem. All right, does the damn thing work? No. Did you mess with it? No. Will you catch hell? No. Trash it. No problem. Once again, did you mess with it? No. Will you catch hell? Yes. You poor idiot. Can you blame someone else? Yes. No problem. I love this. Did you mess with it? No. You idiot. Does anyone know? No. Hide it. No problem. Does anyone know? Yes. You poor idiot. Can you blame someone else? Yes. No problem. There you go. That's how you solve problems at work. Yeah, this has been around, like I said, this has been around since I remember in the 1970s. It's probably was been around before then, but it's fun. It's kind of a nice way.
Terrible.
Yeah, it's kind of a nice way to end our discussion this evening. So what I'm going to say to you guys is make sure you set a block of time for doing the test. Start the test. You have any resource you wish, except you can't copy answers from the internet. I will know that. That'll be the one thing that you will get 0 points here on these essays. Okay, any last minute questions? We're going to leave off about a half hour early, which is okay. A lot of times we'll do this. Just to make sure, for one last time, we are allowed to rewrite the answer in our own words. Yes. Can you do both options of tests? I don't know what you mean by that, Steve. There's only one optional test. There's one required and one optional. There is no optional with test 1. Test 1 is the 45 points from test 1 are from those 3 areas. 5 true and false worth 5 points. 5 multiple choice worth 5 points, 3 points each, and 5 essays worth 5 points each. That totals 45. So you can not do any of those, but you're going to lose points. The optional one you don't have to do, but if you do, you get extra credit. I could stick around, sure, as long as somebody needs something, sure. Sure, Megan. How many questions are on the optional test? Believe it or not, Fawad, there's one. One question, and it's an essay question. And the same thing applies to this essay question. It can't be a copy from the internet. But if you guys were really paying attention this evening, which I think you were, I answered that question. Any other questions? You guys are real good. I really appreciate your participation. It makes this fun. Okay, well, I'll hang around for a little bit if Megan has a question or any of you guys have questions. But we'll kind of just stop our presentation and have a great weekend. And good luck with the test. My wife is telling me what to tell you guys. Thank you. All right, I'll hang around for a little bit, but I'm going to stop desktop sharing. Good night to all of you guys. Yes, Mega. Is this something I could record or not record? Okay, I'll turn off the recording.